Okay. All right, guys. I welcome you all to week 8's contents. And as you know, what we shall do is basically we'll start off by revising what we did in the last week, and then we'll proceed with the contents of this week. So, okay. So what we saw is in the previous week, we looked into the case of something which is known as unsteady heat transfer. And as we saw, the most simplistic and kind of like uh, the most practical scenario, I would say, of this unsteady heat conduction is the lumped capacitance model, as we saw, where the very assumption that we took is that the temperature field inside the body was considered to be uniform, or you can say it's spatially not varying with space. And we saw that the field, which is basically a temperature field, was just a function of time. And we argued that this very assumption that we took is because of the fact that our bio number was less than a certain value. That value was precisely like we took it to be around zero point 0.1. So we saw that when the bio number was less than zero point 0.1, the resistance inside the body, which is typically due to conduction, is very much negligible to the resistance. Uh, it's very much negligible to the resistance that basically occurs from the interface to the ambient, which is by convection. So we established that the ratio of this bio number uh, by doing, of course, by doing a steady state analysis, keeping in mind the fact that the conduction fluxes become equal to the convective fluxes at steady state, we argued that the bio number uh, came out to be the ratio of, so yeah, we came out to be the ratio of the temperature differences within the body divided by the temperature difference that arises from the interface of the body to the ambient. And we said that when the bio number was less than zero point 0.1, this temperature difference is very much less than this temperature difference which arises due to the convective fluxes. So this hinted us to the fact that now our temperature profile would be uniform in space, and we could just assume the temperature profile of the body to be just a function of time. And such bodies, as we saw, are known as lumped bodies, typically because I didn't say this in the last time. So what we saw, what you can establish is that the expression for the temperature field that we saw, that is basically this expression, that theta by theta I is equal to exponent of time divided by the time constant. You can rewrite this expression in terms of a resistance capacitance like framework, just like you do in a typical RC circuit in electrical analogy. Okay, so that's why this model also happened to be known as the lumped capacitance model. And we saw that in this lumped capacitance model, but just by using a simple energy balance, the temperature field came out to be varying, or you can say the temperature field typically exponentially decays with time. And of course, the expression is somewhat like this: theta by theta I is equal to the difference of t minus t infinity by ti minus t infinity, where this t happen to be our variable, which is now just a function of time, and it is of course equal to the exponent of minus t by tc. We saw that this expression can be equally written in terms of the bio number and the Fourier number, and this happened to be written as exponent of minus times the bio number into Fourier number, where this Fourier number came out to be the ratio of the inherent time scale of the problem to the diffusion time scale. Okay. And just like the bio number is a non-dimensional number, you can also appreciate that the Fourier number, which is just the ratio of two time scale, is also a non-dimensional number. Okay. Now, this was the background that we developed when we studied the lump capacitance model. So what we did is we basically solved the problem involving or using this lump capacitance model, uh, where we solved basically this problem, where we saw that where basically we dropped some steel balls which were at some higher temperature and then subsequently cooled in a environment which has a temperature less than which whose temperature is very much less than the ambient temperature. And we saw that, so we were asked basically to evaluate the time required for cooling, required for the entire cooling process. So we started off by first evaluating the bio number, and since the bio number came to be less than zero point 0.1, we argued that the lump capacitance model can now be applied. And then we simply use the expression for the lump capacitance analysis to basically calculate the time required to cool the balls, basically. Okay. However, in one of the next problem, we saw that even though like we can assume an object to be a lumped object, but using directly the expression of the temperature, which is exponentially decaying with time, can sometimes lead to wrong results, because in this case we saw that we established this numerical because of that, and we saw that whenever there is a heat generation taking place inside the body, we cannot, although it can be assumed that the temperature field is varying, the temperature field is just the uniform in space and it is just varying with time, but still you cannot directly apply the formula that we develop for the lump body, that is theta by theta I is equal to exponent of minus T by Tc, typically because there was heat generation taking place inside the body. So just by doing a simple energy balance, you can see that there is an extra term that comes because of the heat generation. And this is something that we studied. Okay. And then we saw that the temperature profile, the governing equation that the temperature profile followed was although it was a first order, it was our first order in nature, it was typically a non-homogeneous governing equation. Okay, which you can see just directly from here, because if you put t to be equal to 0, you still regain a non-zero part in the right hand side. So we saw how to basically solve these kind of governing equations, which are first order. Of course, they are linear, but they are non-homogeneous. And we looked into something which is known as the integrating factor. And just by calculating this integrating factor, you can write the solution or the answer in terms of the integrating factor, uh, as we saw in the last class. Okay, so this is something that we did in the last class. Today, as I said, before actually proceeding to the contents of this week, I will quickly discuss something which is known as a semi-infinite solid, because this is something that comes under transient heat conduction. And it's kind of the others, you can say it's kind of, it's at the other end of the spectrum of transient heat conduction. So it's like, while the lump capacitor analysis, is typically valid when the temperature field is not a function of your space, the semi-infinite solid, on the other way around, is valid for it. So as the name suggests, it's valid for semi-infinite bodies, which means now you cannot assume that your temperature field is just a function of time. So it now becomes that you need to solve your temperature field as a function of space as well as a function of time. And such bodies, okay, where you use this transient heat transfer analysis, where your temperature field is now a function of space as well as a function of time, are known as semi-infinite bodies. Okay. So we will quickly see the semi-infinite solids or bodies and the heat transfer associated with it. And then we will proceed to the topics of today's, of this week's discussion, which basically is the numerical methods. So we will see what these numerical methods actually mean, and we will see that these are indeed helpful tools to sometimes calculate the temperature field in an approximate way. Okay, we will see all these things, but first we will learn what is essentially a semi-infinite solid, and a simple numerical associated with this semi-infinite solid. And then we will proceed with the numerical methods, that is using simple, say, schemes like finite difference schemes to typically, solving the heat transfer equations that we saw. Okay, so this is the agenda for this class. I will stop here for some time. If you have any doubts related to the assignments, or the last lectures or the interactive sessions as a whole, you can feel free to ask me. Okay, or else we will start off with today's discussion. In the meantime, I'll just check if the recording is in progress or not. It's running on. Okay, all right. So if no questions, let's start off with something which is known as the semi-infinite solid. I'll start off by just giving a simple example where we can basically use this concept of a semi-infinite solid and a similarity. So the solution of finding the temperature field of a semi-infinite body is by something which is known as using a similarity variable, and we will quickly see what this similarity variable and why are we supposed to use this similarity variable very shortly. But before that, let's try to like frame the physical picture of the problem. So for instance, let's say I have a body whose dimension in say the y coordinate is finite. For instance, let let us say this axis let us say this axis is y, and this object has a finite dimension in the y direction. However, in the x direction, I say that this object's length is typically very large than its width, which means that the dimension in the x direction is very much larger than the dimension in the y direction. Okay. Now you can assume, of course, this object as a 3D object also, just by extending it in the other direction. But we will neglect the 3D effects, so we will just consider this object as a two-dimensional object only. But you can still extend its dimension in the other dimension as well. Extend its width in the other direction as well. Okay. So the thing is, now if I, let's say, this object that I basically drew here, you can like think of it like a wall whose let's say the height is very much less than its length. Okay, such kind of object you can interpret as a semi-infinite object. Okay, so what I was trying to say is, let's say at time t, let's say at time t equal to 0, I consider that the temperature of this object, which will now be a function of space, it will, so the temperature field will now be a function of x. Okay, where your x direction is in this direction, where your x direction is in this direction. So it says that your temperature field, okay, which is now a function of x, and at time t equal to 0, it's some Ti. This means you can assume that, let's say, you know the initial temperature of this object. For instance, let's say you are keeping a brick in a room. You know that at time t equal to 0, okay, the temperature of the brick is basically equal to the temperature of the ambient, which you can assume, let's say, equal to some T infinity. Okay. Now, let's say what we are doing is we are subjecting one face of this object, which let's say is this face with let's say some prescribed temperature. We call it some T naught. Okay. Where this T naught is much higher. Let's say it's much higher than Ti. It doesn't actually matter, but let's say we are considering, for the sake of like clarity, we are considering that this T naught is much greater than the ambient temperature. For instance, let's say you are keeping a brick, okay, so you're picking up a brick from a room which is at a which is kind of at ambient, or which is kind of at an ambient temperature, and you are placing that brick into a furnace. So when you are placing that brick into a furnace, let's say you are placing one of the faces of that brick into a furnace. So what will happen is the temperature of this face, okay, is now basically subjected, okay, the temperature of this face is now basically subjected, okay, to a temperature which is much higher than the room temperature. So what will happen as a result of this? Okay, so what basically will happen is your temperature front, okay, will propagate inside the object. For instance, let's say after time t equal to some t1, if I draw the temperature profile inside this object, let's say it's a brick, then my profile would be something like this. Okay, where you can assume that this is some T infinity, and this is some, so this would be basically equal to the T naught. Okay, and this is true for some time T1. Okay, so what it means is that, let's say after time, let's say I pick T1 to be equal to 2 seconds. This means that the disturbance means the addition of this temperature that is prescribed in one phase will propagate up to a distance, let's say x1. So this distance, I will consider it as some x1. Okay. So meaning that the physical meaning of this propagation of this conduction wave front, this is typically what is said in heat transfer language. So it means that up to time t1, the message that it establishes that there is a prescribed temperature onto one of his face is propagated to a distance x1, and after x1 it still does not know, okay, that there is a prescribed temperature or there is a disturbance that is being imparted into one of his faces. Okay, such kind of mechanism is seen in a semi-infinite body. Okay, if this body is a finite body, you cannot argue that your conduction wavefront would basically vary spatially like this. Okay, now let's say at the given time step, let's say I increase my time step now, so I move from a time t2 which is greater than t1. You can appreciate that the conduction wavefront would now move further up into the other dimension of the body. For instance, if I now draw the temperature profile, it would be something like this. Okay, now this would be T infinity, and this is for some time T2. Okay, and this now, so now you can see that the conduction, so this wavefront, that is the conduction wavefront, has moved further inside the body, and now this distance you can assume it some x2. Okay, all right. So as you can see that there is an inherent relationship between the time, okay, and the distance up to which the conduction wavefront has propagated. Okay, and this inherent, so you can, so that just by doing a simple order of magnitude analysis, you can eventually so that this distance of propagation, generally it is known as delta. So this x, people generally call it as delta, which is the distance of propagation up to which the disturbance has propagated inside a semi-infinite body. It is shown that this delta is proportional to square root of alpha times t. Okay, where this alpha is basically the thermal diffusivity of the object. So this alpha, as you know, is basically the thermal diffusivity. So it can be shown that this distance of propagation is proportional to the square root of alpha times t. And this can be very easily shown. For instance, if I just write down the governing equation for this object, the governing equation would be what? It would be just del square t by del x square. Okay, this is, you know, this is, so can you just tell me the other terms of this governing equation? What would be the governing equation that determines how the temperature field would look like inside this semi-infinite object? Can you tell me? This is del square t by del x square. What would be in the right hand side? Can you give it a try? Yes, any suggestions on this? This is simple, right? So remember, now my temperature field would be just a function of x and t, okay? Which means that, of course, you need to appreciate that this is not a steady state problem, because as you can see, as you go on increase, so your basically conduction front is a function of space and it's a function of time as well. Okay, so it's no longer, you know, a steady state problem. So what would be this on the right hand side? What would be this? I mean, we saw this multiple times, right? So this is simple, right? So this is just so if I write down the heat diffusion equation, it becomes what? It becomes K times del 2T by del x2. This is equal to rho Cp times del T del T. Okay, where now this T is a function of x and time both, which was not the case in case of in case of this thing of a lump capacitance object. Okay, now you can show that. So basically, this, if you bring this K to the other side, it becomes del square T by del x square, and this becomes equal to rho Cp by K times del T del T. And you saw that this ratio of K by rho Cp, as we saw it in the last class, this is known as the thermal diffusivity. So this becomes 1 by alpha times del T del T. Okay. Now, if you are just aware of some basic, order of magnitude analysis, or at least you know how to basically scale certain terms in a differential equation, then you can say that these term del square t by del x square, you can say that this scales as, okay, some characteristic temperature divided by delta square, where delta is that same delta that which denotes the distance up to which your conduction wavefront has propagated. Okay, and these term, the term, so this is what these term scale says. Okay, for instance, the other terms 1 by alpha del t by delta t, this you can say it scale says some characteristic temperature times alpha divided by the characteristic time, or let's say it's just the time. Okay, I hope like you are with me on this so far. So since these terms are now equal, okay, for instance, this term is equal to this term, so you can say that the order of magnitude of this term will also be of the similar order to the order of magnitude of the other term, which means I can just write that this Tc by delta square is of the same order of Tc by alpha d. So Tc and Tc get cancelled, and then you can show that your delta square is of the same order of alpha t, or you can say that your delta is of the same order of square root of alpha t. And this is something that I have already said to you some time ago, that so what this means is that your distance of propagation, okay, your distance of propagation of this conduction wavefront, it is not just a mere arbitrary like value, but it is somewhat related to the time up to which you are exposing the semi-infinite body to the disturbance. Okay, which means, so this means that, so can you just tell me one quick thing, what does it mean? So it means that your variables, which for instance in my case my variables are x and t, so you can just say that at a given x, okay, which is so delta and x is just the similar thing, okay, people generally denote it as delta, and that's why I also denote it as delta, but it's the same thing, it just denotes the distance up to which your temperature field has propagated. Okay, so you can say that this x, okay, that is the distance up to which the conduction wavefront has propagated, is kind of proportional to the square root of alpha times t, which means your independent variables in your problems, which are just x and t, are somewhat related to one another. Okay, and this you can interpret as a good recipe for using the method which is known as the similarity solution. Because in similarity solution, you define a similarity variable, let's say eta, which relates how the quantities, that is the independent variables, are linked to one another. For instance, if we use a similarity variable here, let's say eta, you can define eta as by some square root of, so you can define it by x by square root of alpha times t. Okay, so the idea is that so why do we use similarity variable is basically something that we need to understand it from here. Okay, so we are using, as I repeat, we are using this similarity variable solely because we know that, so if we can establish, if you can establish a link between how my independent variables are indirectly related to one another. Okay, so if I can do that, I can define something which is known as a similarity variable. Okay, and then what we do is we use this similarity variable to basically solve this governing equation. Okay, again, the idea is that we kind of use this variable, write this governing equation in terms of this similarity variable, which converts this partial differential equation into an ordinary differential equation. And this is something that we follow, just like how we solve for when we use something which is known as the method of variable separation. Remember, in the method of variable separation, okay, our independent variables were x and y, if you remember, because we just solved the Laplace equation. That's it. Okay, so if you just remember some 2 classes back, we use something which is known as the method of variable separation to basically solve a 2D Laplace equation. And this Laplace equation was just del square t equal to 0, which you, if you remember, it denoted how my temperature field would basically vary in a 2D, let's say, rectangular slab, for instance. Okay, but in that example, we could not use the similarity solution typically because my x and y were not linked to one another. Okay, I cannot say that my x is some proportional to some square root of y. I cannot say that. And since I cannot like establish a link between my independent variable, I could not use the similarity solution. But here, since I know that the distance up to which my conduction wavefront would propagate inside a semi-infinite body is basically proportional to its thermal diffusivity, to the square root of its thermal diffusivity times the temperature up to which, we are just keeping this phase attached to the disturbance. Okay, since we know that, we can use something which is known as the similarity variable. So I will not show the solution here. You have already like derived that in the lecture classes, but this is the basic idea. Why do we use the similarity solution? Okay, so if you remember, if you just solve this partial differential equation using this similarity variable, you came up, okay, with the form of the temperature field as something like this. So I think you will remember. So your temperature field was something like this, because t as a function of x and t, this is something that you evaluated, minus t naught divided by ti minus t naught, that is equal to, okay, now can you tell me what is this? This is something that we have seen, right? Can you tell me what is this? What is this ERF known as in the language of mathematics? Can you tell me? Yeah, exactly. This is the error function. Okay, that's exactly correct. Okay, so you saw that your temperature field. Okay, now can you tell me what was this? What is this? X by square root of alpha t. We just established. We just saw it some seconds ago. So x by square root of alpha t is the similarity variable, right? Which you yes, exactly. It's eta basically. It's not n, it's eta. Yes. So you saw that basically just so I have not shown you the derivation of this of how the temperature field is linked to the error function of the similarity variable. Okay, but that's just the derivation. You can just have a look in the lecture classes video because it will just eat up the time if we just start doing the derivation. But the idea is that you can establish your temperature field in terms of the in terms of the similarity variable, or because you know that your similarity variable eta is nothing but just x by square root of alpha t. Okay, and then you can just substitute this form of eta and get your answer in terms of x and alpha t. Okay, or so the idea is that you can either write this in terms of eta, or you can just write this in terms of x and time, which are the two independent variables that we are kind of looking at. Okay, so this is the temperature profile. Okay, this is the temperature profile that you guys have derived using again something which is known as the similarity variable approach. I repeat, the motivation for using the similarity variable comes from the fact that you know how your distance of propagation would evolve with time. And you have a kind of rough order of magnitude estimation that your delta or x, that is the distance of propagation, it varies as square root of alpha times t. But remember, x is not exactly equal to square root of alpha times t, as you can see from here. We are just doing an order of magnitude analysis to just get a knowledge of the ballpark figure that the x, that how this distance of propagation would vary as the time. Okay. All right, guys. So this is something that is related to the similarity variable and the temperature profile temperature profile associated with this semi-infinite solid. Now we'll do a quick question on on this semi-infinite solid, and then we'll close this discussion. So it says that there is a thick slab. Okay. So it says that there is a thick slab. The term thick here denotes that like the dimension inside the slab, you know the direction through which the heat transfer is taking place. Okay, this direction is basically it's long enough such that you can use the similarity solution that we just saw. So it says that a thick slab of some properties is initially at 300 degrees Celsius, which means that my Ti is equal to 300 degrees Celsius, and it is cooled by water jets impinging on one of its surface. Just like we saw the last physical picture where we say that the one face is subjected to a higher temperature. Now it's the other way around. It says that the slab which was initially at some higher temperature, it is now being cooled, by bombarding these water jets into one of its faces. For instance, you are just spraying water jets like this onto its faces. Okay, so this means that you kind of know that what basically the temperature on this face. Okay, and you can assume that this slab is thick enough such that it falls into the realm of similarity solution. Okay, so it says that the initial temperature is Ti. The temperature of the water, that it says that, so this you can assume that this surface temperature, at least you can say it's 25 degrees Celsius, and kind of neglect that there is any convection loss in between this surface and the water, which means that the water temperature typically happens to be the surface temperature. And and it says that the temperature of the jet is 25 degrees Celsius. That's okay. And the jet maintains an extremely large, approximately uniform convection heat transfer convection coefficient on the surface. Assuming that the surface is maintained at the temperature of the water throughout the cooling, which says that this surface is now at 25 degrees Celsius, they are asking how long will it take for a temperature to reach 50 degrees Celsius at a distance of 25 mm from the surface. So they are asking that if you go up to a distance of 25 mm from the surface, okay, how long will it take for this surface to reach 50 degrees Celsius? Okay, that is what they're asking. All right. So the answer is simple. You just use the temperature profile of the semi-infinite solid that we just saw, which says that which is basically this. Okay, which is basically this. So it is. So if you just write, it is what? It is just t as a function of x and t minus t naught by what? It is ti minus t naught. Okay, it is just I minus t naught, and it is equal to the error function of x by 2 square root of alpha t. Okay, now you know everything. You just need to figure out this time t. So so what you can do is, so you know this temperature, it's given to be equal to 50 degrees Celsius. That, so what is given at you need to find x when your time is basically 50 degrees Celsius. Sorry, I'm sorry. You need to find your time where your temperature at x equal to 25 mm is equal to 50 degrees Celsius. So you can just substitute this as 50. T naught is basically the temperature of the phase, okay, on which you are impinging the water. So this T naught is equal to T surface, which is equal to 25. Ti is the initial temperature. Initial temperature was given to be equal to 300 minus T naught, which is equal to 25. And then you know this is error function of x. The only thing is that you need to write x in meters. So this x is equal to 25. So this x becomes equal to what? It becomes 25 into 10 to the power minus 3. Okay, divided by 2 times square root of alpha t, where alpha you can just calculate from this given knowledge, because you know rho, you know c, and you know k. So your alpha is nothing but k divided by rho c. So your k is what? Your k is 50, rho is 7,800, and c is 450. Everything is in SI unit. So it is 50 by your rho is what? 7,800 into C, the heat capacity being 480. So just calculate alpha from this. Okay. So you just know everything. You just need to figure out this time t. So now, how do you, so this is not this is not so straightforward, because what you now need to do is you need to take the error function complete. You need to bring this error function to the other side. This is done by doing something which is known as the error function complement. Okay. So you just need to evaluate this value and then see what is the error function complement of this value. Okay, and when you know the error function complement of this value, you can just calculate what will be the time from here. I hope you understood what I mean to say. Actually, I don't have the error function table with me, so error function complement table with me rather. That's why I cannot pinpointedly say the answer, but I think you got the gist of how to basically solve this problem. So that's very simple, right? Because you need to calculate time, which means you need to bring this error function kind of to the other side. So the way it is done, systematically is like calculating this first, calculate this fraction first, and calculate the error function complement of this fraction. Okay, so if you know the error function complement of this fraction, then this just becomes equal to your 25 into 10 to the power minus 3 by 2 times square root of alpha t, where alpha you already know. So from here you can just calculate time. So did you understood? Can you just give it with an yes or a no? Did you understood how to basically calculate time by using something which is known as the error function complement? So yes, okay, thank you very much. Okay, all right, guys. So this ends. So I'll stop here for some time, and this ends our discussion on something which is known as transient heat conduction using. So we looked into two things. First, the lump capacitance model, which we looked it extensively. Maybe because of the fact that most of the physics of heat transfer in transient conduction comes in can be like modeled as a lump body. And then we also saw something which is known as this semi-infinite solid, where we saw that you can use something which is known as the similarity solution to basically come out with the solution of your temperature field as something like this. And we saw that what is the reason behind why you are using this similarity solution. Typically because I know how my length scale is related to the time scale of the problem, at least by an order of magnitude analysis. Okay, with this we stop the discussion on these two aspects, and now we'll move into something which is known as numerical methods. That is, we'll look. So I'll explain to you what numerical methods are. But before that, like, if you have any questions, you can ask me, or else, like, I just come in 2 minutes by filling my cup with water, and then if you have any questions, you can ask me, or else we will start off with something which is known as the numerical methods. Okay, but yeah, if you have any questions up to this, you can either write it in the chat. Let's see if there are any questions. Okay, so you can just write it in the chat, or you can just unmute and speak. I'll just come into hands. Okay, all right. Sorry for the interruption, but yeah. So if you have any questions, you can just put forward here questions not only on this aspect, but like on the previous aspects as well. So I hope at least attending these sessions will is little bit helpful for you in solving the assignments as well. Uh, Again, the goal is that not to directly disclose the answers of the assignment, because that would just not serve the purpose, but give you some hints while we go through this learning thing, and then which will of course be helpful for you to just understand the subject, and also like give you some hints at least to solve the problems of your assignment. Okay, so if you kind of look into the website of the course, you will see that this week's assignment is primarily on numerical methods, and we will discuss some nuances of this numerical methods, and again it will surely be helpful to you for solving the assignments as well. Okay, but yeah, directly like solving the problems of the assignment won't serve the purpose, because it just become a typical spoon feeding approach. Okay, which we will not do you know in these sessions. All right. If no other questions, what we will do is we will close the discussion on this semi-infinite body and the lump body, and we will move forward into something which is known as the numerical approach to solving heat transfer equations. Okay, and the very idea of these numerical methods, as we will see very shortly, is that they are easy. First of all, for instance, okay, we will just have a look into something which is, so we'll recap, we will revisit the two-dimensional steady state heat conduction equation. And if you remember, we solved that. So can you tell me what was the method that we used to basically solve the 2D steady heat conduction equation without any heat generation? I just stated that, but can you recollect what did you use to get into the approximate, so to get into the exact solutions? So we did this 2 classes back, if you remember. Like, so we solved this equation del square t equal to 0, which was basically the Laplace equation, which governs how my temperature would vary for a 2D scenario, considering it to be a steady state and without any heat generation. Okay. Yes, we use safe factor analysis. True. Safe factor analysis, I would say it's a special case of this 2D heat transfer. But if you remember, the most general case that we discussed was something which is known as method of separation of variable. Do you recollect? So what we say is that, yes, exactly. So what we did is that we did we assume that my temperature profile will be just some function of x times some function of y. Okay. And then what we said is that we substitute this into the governing equation, and this analysis resulted in the evaluation of something which is known as the eigenvalue. And we saw that just for some specific values of this specific, terms of this eigenvalue, we could write a series solution of the temperature field. So if you remember, my series solution came as the summation of the modes. The modes started from n equal to 0 to infinity. It has some sine modes, it has some sine hyperbolic modes, if you remember. Okay. So, do you recollect these solutions? Like, do you remember that the entire solution? So, yes, exactly. But if you remember, we took, so this method, although this being an exact method, the method of, so the method, let's say the method of separation of variable, or let's say the method that we learned today, that is by using similarity solution, although we did not derive the solution, you can at least appreciate that these are very long and tedious method. At least when we looked into the solution of the method of separation of variable, we spend around at least, 30, just some 30 minutes to basically come into the steady state temperature profile for a special case, at least when we saw that, the temperature at the faces were homogeneous. And then I said that when it was not homogeneous, we need to take some transformation, to make the paradigm into the framework of this method of separation of variable. So, since these methods, although they are very powerful, as I said, because they are exact methods, but sometimes these methods turn out to be very tedious. For instance, let's say I want to calculate the temperature on a face where let's say on this face I have some fluxes known. Let's say I know what is del t by del x here. On this face, let's say I know what is del t by del y, which is just some arbitrary, and some other conditions here and here. So it is very difficult for us to frame that problem into the method of separation of variable, typically because first of all, although my governing equation is homogeneous and it's linear, but the boundary conditions is no longer homogeneous. And you can see that even though you establish a lot of transformation, it becomes very difficult to make the framework fall into the framework of this, what we call this method of separation of variable, or the similarity solution. So easy and you can say it's easy, and although it is approximate, it is very powerful. So this method, which is easy, of course, and although it's an approximate method, as I said, it's very powerful. These kind of methods are known as numerical solution. So the idea is that what you do is you kind of use an approximate solution of the derivatives of the differential equation to transform the differential equation into an algebraic equation. And this is something that we will see how this transformation is done. Okay. For instance, if you have a 2D steady state conduction, the governing equations, if you remember, that we solve, the governing equations that we solve was something like this. So it was del square t by del x square plus del square t by del y square is equal to 0. Okay, so this is precisely the governing equation that we solve, subjected to some boundary condition. Now we solve this equation, if you remember, by as I said repeatedly, we solve this equation by something which is known as the method of separation of variable. But we will not do it now. We will use the numerical method to basically solve this equation. And how this is done is, what you do is, let's say you are solving this equation. Okay, let's say you are just solving this equation for this entire body, and you want to determine the temperature field inside this entire body, provided you know some boundary condition, that you know how the temperature field would vary along its surface. Okay, let's say for this instance, you know a priori what is the boundary condition, and this is always the case, because boundary conditions always come up with the problem statement that you are given. Okay, it's not that you need to solve the governing equation without knowing the boundary condition. That is just not possible. Okay, so the idea is, let's say you know the boundary condition of this geometry, although this is an arbitrary geometry. The idea is, if you know the boundary condition, how do we use numerical methods to basically evaluate the temperature field inside this body? Okay, yeah, but now you cannot use the method of separation of variable. So what you do is, typically what people do is, they divide this entire body into very thin domains. Okay, they divide this entire body into these thin domains, and what they do is they try to evaluate the temperature field on each of these points. These points in the language of numerical methods are known as grid points. Okay, so what they try. So you can appreciate that the finer is my domain. Okay, the finer is the division, the more accurate your temperature field would be. Okay, for instance, if I just make two divisions like this, okay, if I just make kind of like two divisions like this, of course my temperature field is now just defined on these nodes and these nodes and these nodes. That means it's kind of just a sparse, it's kind of just a sparse grid that I made. So now naturally my solution will not be accurate. However, if I divide this domain into a very thin grid, into many very thin grid points, then the temperature field at each and every grid points, so the grid points are now so close that the temperature field, if you still evaluate it at each and every grid point, it kind of tends to being a continuous distribution. I hope you can understand what I'm trying to say here. Okay. So this is the very essence of using the numerical method. Okay. So now what they do is once you, so as I said, the idea is to basically evaluate the temperature field at each and every grid points. And so what you do is you kind of divide these grid points. Okay. Divide the domain into many grid points. And then what you do is you kind of write these governing equations at each and every grid points. Okay. So you map these governing equations at these grid points. So the idea is you convert these governing equations into an algebraic equations valid at each and every grid points. And then what you need to do is you just need to solve that algebraic equation to basically find the temperature at each and every points in the grid. This is the whole idea behind this numerical method. Okay. Now, 1 second. Okay. So now the natural question arises that how can you map this equation into these grid points? Okay. So this is done by using what is known as the Taylor series expansion, and this is already shown into this week's lecture classes. How do you basically write this second derivative into a algebraic equation? This is done by using the Taylor series method. You can check the lecture videos on that. I'll not do the derivation on this aspect, but I will show you that how do you basically get the end result on when you kind of, let's say, convert this second derivative into algebraic equation. So for that, what people do is they kind of pick up any generic grid. Okay, let's say I pick up any generic grid, let's say Mn. Okay, so when I pick up this generic grid Mn, this grid basically looks something like this. And I also see how my neighboring grids would look like. So for instance, so first of all, I have chosen m number of grids in the x direction. Okay, and I have chosen n number of grids in the y direction. So can you tell me what will be the total number of grids in this 2D space? If there are m grids in the x direction, so I'll write it down. So I have chosen m grids in x direction, and I have chosen n grids in y. Okay, so now based on this, can you tell me how many grids will be there in the total space? That's simple, right? Can you tell me? So I repeat, let's say I have chosen m number of grids in my x, and then I have chosen n number of grids in my y. Then in my total space, can you tell me how many grids will be there? What is the total number of grids that will be there in my total 2D space? So it is just m times n, right? That's typically is what it should be. Okay, so the total number of grids will be just m times n. And what I need to do is I need to frame m times n algebraic equation in these grids, and then just basically solve for a temperature into this m times n grid. That's the only thing that we need to do. Okay, so so what people do is they kind of just pick one generic grid. Let's say this is the grid that I'm picking up. This grid has a coordinate of, let's say, m and n. Okay, where this m and n is just a generic number. Okay, so this grid becomes m plus 1 times n, and this becomes m minus 1 times f, because when I'm moving from this to this grid, I'm keeping my y constant, and I'm just changing my x. So that's why the yth number is just n, and the x number has just an increment by 1. And what I do is the distance between these two grids, I name it as delta x. And similarly, the same analogy is drawn in the y direction. For instance, these grids now becomes m, n plus 1, and this grid now becomes m, n minus 1. and the distance between these two grids, I consider it as delta y. So, I repeat, what do we do? So we pick out any generic grid Mn. Remember, this Mn is just a generic grid that I'm considering. Okay. So once I know, this grid is basically the target grid that I am first considering to write down the governing equation on this grid. So what I will do is I'll try to write this governing equation in on this very grid point. So in doing so, what I also need is I also need to know what is the number of the neighboring grid points. So the neighboring grid points, is named as like, it's not the, so you can interpret this, if these grid points is m comma n, this grid point becomes m plus 1 comma n, and so long the other, so is the other grid points, drawing the same analogy. Okay, now can you tell me how do I write this del 2t by del x2, okay, in terms of the temperatures at these grid points? Because the idea is that I need to now transform this second order PDE into an algebraic equation. So can you tell me how do I write? There is something which is known as central difference scheme, a forward difference scheme in finite difference method. So do you know what is, how can I write this del 2t by del x2 in terms of the temperatures at at these grid points basically? So since I need to write del 2t by del x2, I need to check what is the gradient along this x direction. Therefore, it now becomes, I need to write the temperature of these grid point in terms of this and the other grid points. So if you remember, or if you at least saw the lecture series, this del 2t by del x2, okay, this can be written as t at m plus 1 comma n minus 2 times of t m comma n minus 2 times of t, this is plus 2 times of t m minus 1 comma n divided by delta x squared. Okay, did you kind of see some such kind of expression in like before? Or like, so are you accustomed to these kind of like expressions? Oh, okay. Okay. So yeah, so what I would suggest it, so I'll not just go into the detailed, derivation of this. I would suggest it like this has been done in this week's, lecture series. So kindly just go back and just visit this week's lecture series. So you will get to know this detailed expression of how this is basically derived. Is it okay? Because like if I start from deriving how this, so this comes from the Taylor series expansion. Okay, yeah, yeah, okay, thank you. So this comes basically from the Taylor series expansion, but it will take some time to basically show you how to, how to get this from this form of the PD. So basically, as you can see, we have kind of transformed this derivative of temperature into these grid points, as you can see. Okay, and this is the so again, this is done by using the Taylor series method. And in fact, this is one of the questions of your assignment. What is the logic behind using this finite difference method? By the way, this method is known as the finite difference method. Okay, I have not said the name. This name is known as the finite difference. This method is known as the finite difference method. Okay, typically, because so there are many other methods. Okay, of of using, so there are many other numerical methods. For instance, there is a method which is known as finite volume method, where in finite volume you don't define the grid points, you define something. So you define something which are known as cells. Okay, in finite volume method, instead of writing the equation at grid points, you write the equation at cell centers, just like this. Okay, so this is where, so in heat transfer, the finite difference method also works well. But if you are solving problems of fluid mechanics and heat transfer together, you need to use, or if at least your problems is complicated in nature, you need to use something which is known as finite volume method. If you are aware of softwares like like ANSYS or COMSOL, if you are aware of these softwares, so if you kind of try to understand how these softwares basically solve you the answer, they typically use these numerical methods only. For instance, if I am not wrong, ANSYS uses finite volume method. Okay, and softwares like COMSOL uses something, so uses another type of this numerical method which is known as finite element method. Okay, so yeah, so if you run this software, you just get the answer, but at the back end of this software, these are the things that basically goes on. Okay, anyways, so again, the idea is that you need to write the temperature field here into these many grid points. Okay. So for instance, this del 2 T by del x2 can be written something like this. In the same analogy, drawing the same analogy, you can write this del 2 T by del y2 as something like this. So now what it would be? It would be T of m comma n plus 1, because now you need to write it in the y direction. So your grid points would be this point, and this point. Okay. So it would be T of m comma n plus 1 minus 2 times of T of mn. Okay. Plus, can you tell me what would be this term? Drawing the same analogy here. What would be this term? Any So I understand you are learning it first, but at least drawing the analogy from here and here, can you tell me what would be these terms? Any suggestions? Yeah, it will be exactly. It will be t of m comma n minus 1. Exactly. It will be t of m comma n minus 1 divided by what? Can you tell me what would be this? Keeping this picture in mind. It would be just delta y square. Yes, exactly. Delta y square. Exactly. It would be just delta y square. All right. So this very method of converting the differential equation into an algebraic equation is known as discretization. And what we basically did is we have discretized the differential equation into a set of algebraic equation. Now, why is it called a set of algebraic equation? I'll tell you why. But at least you need to understand that from having a derivative like del 2 t by del x2, we have used some approximate analysis to basically come out into the temperature field directly. So as you can see, these are just temperature, right? It does not involve any derivatives. As you can see, these are just temperature. So where you are evaluating the temperature, you are evaluating the temperature at the grid points. But at least what you did is you had transformed the differential equation, okay, into an algebraic equation where your temperature field is now written at the different grid points. Okay. So now if I just substitute, if I just substitute this here, substitute these two here, what we will get? We will basically get okay, we'll basically get what? We'll just get t at m plus 1 comma n minus 2 times of t at mn, okay, plus t at m minus 1 comma n divided by delta x squared plus what? You will get this term is t at m comma n plus 1 minus 2 times of t m comma n plus the other term, which is t m comma n minus 1. Okay, this is the other term, and then this is divided by delta y square. Okay, and now if I just assume that the distance between the two grids in the x-axis is equal to the distance between the two grids in the y-axis. If I just assume this simple assumption, which means that delta x is typically equal to delta y, then I can show that this algebraic equation, in fact, this is very simple. This delta x now becomes equals to delta y. So, and of course, this is equal to 0. That is typically because I have a 0 in the right hand side. So this now equations can be written as t of m plus 1 comma n, okay, plus t of m minus 1 comma n plus t of m comma n plus 1 plus t of m comma n minus 1 minus 4 times of t of m comma n, and this is equal to 0. Okay. So what you did is, obviously, because considering the assumption that your delta x is basically equal to delta y. Okay. So what you did is you have transformed your differential equation into an algebraic equation defined at each and every grid points using the method of discretization of finite difference basically. Okay. So if you see, this is one of your questions in your assignment where basically you were asked to basically see what would the transformed temperature field would be if you kind of discretize your Laplace equation that we just now saw in 2D space. So the solution is that if you discretize this equation using the 2D finite difference method, you should end up getting this form of the discretized equation. So this equation so this people call this equation as the discretized discretize algebraic equation for the m comma nth grid point. So people use the word grid point, or sometimes people use the word node. Okay. So the idea is that once you get this algebraic equation, so now you can at least appreciate that this is now no longer a partial differential equation. Okay, so what you did is you converted this partial differential equation into an algebraic equation at the m comma nth node. Okay, so the idea is you need to write similar kind of algebraic equation at each and every nodes here in your 2D space, and then basically solve this algebraic equation to get the temperature at the each and every nodes of your analysis. For instance, you can see here that the unknowns. So what are unknowns? Unknowns are these temperatures, right? You don't know these temperatures. Okay, so you need to know, you need to solve for this temperature by writing this equation at each and every nodes in your analysis. This is typically, so by hand, of course, you cannot do this. Okay, at least in 2D scenario, you cannot do this by hand. So people use computers to basically solve these algebraic equations together. Okay, so I will not, this is just so for the sake of the course that you are doing here. This is not a, you know, this is not a computational fluid dynamics course, so we will not go into the details of solving these sets of algebraic equation. So there are methods. For instance, there is a very famous method which is known as a tri-diagonal algorithm method. Of course, you cannot solve this equation using this tri-diagonal algorithm method, but there are other methods, but these are very common methods. For instance, you can solve this using something which is known as Gauss elimination method or a Gauss-Seidel method or something like this. But at least for a 1D case, you can use this tri-diagonal algorithm method, but these are different methods of solving these algebraic equations that you will write at each and every grid points. Okay, we will not go into how this solution is done, but trust me, once you know how this solution is done, then these methods will be just bread and butter for you. I mean, this is much easier than your method of separation of variable, and these are very generic methods. Okay, it does not depend upon what is the boundary conditions that you have, or it doesn't have any limitations on the kind of boundary conditions that you had, which we earlier saw in methods like method of variable separation. But of course, since this is an approximate method, because you are just approximating, so this is not, so this, you cannot directly write this del 2 t by del x2 as equal to this form. This obviously has an error. This error is of the order of delta. So this error is of the order of delta x cube, basically. Okay, so yes, you cannot directly write this as this to be equal to, so your del 2 t by del x2 will not be exactly equal to this because it contains an error. But if you choose your grid points to be very very fine, or the distance between grid points is very less, or like your delta x and delta y are very small, then you can say that the errors which basically arises from these expressions are negligible, and you can kind of approximate this del 2 t by del x2 as just this, as just this form. Okay, so yes, so if you go into, so just have a look at the lecture series of this week, and you will kind of know what are the errors that are associated with these discretizations, and so on and so forth. Okay, so I hope this is clear to you. I understand that if this is the first time that you are saying this, then of course this would be a little bit complicated to you. But trust me, if you kind of make it a habit of like doing this discretization and all, and if you just take into if you just, so there is a course which is known as computational fluid dynamics. Where in this computational fluid dynamics, this is the first thing that people teach. Discretizing using finite difference method. Okay, first, so initially we'll be exposed to discretizing just 1D problems. We have just now discretized a 2D problem, but initially we'll be exposed to discretizing 1D problems using finite difference method and how to basically get the solutions. Because see, we have just now written the algebraic equation. We have not solved the temperature field, right? So there is a one step ahead where you need to basically solve the temperature field from these algebraic equation. And trust me, if you have a little bit knowledge on mathematics, the set of algebraic equations when you write for all the nodes will be of the form a matrix times a vector equal to some other vector, let's say some b vector. Okay, where, so I think you have seen this kind of algebraic expression where you can write the set of algebraic equations as a matrix multiplied by a vector equal to some other vector v, where this vector contains all the temperatures that you need to find. This matrix will be just a set of values. So in order to evaluate this temperature, you just need to take the inverse of this matrix multiplied with b, which is basically a constant vector. Okay, so this is just a way of solving this these algebraic expressions. Okay, all right, guys. So this is a discretization method where we have used a spatial discretization of this so-called Laplace equation. Okay, to basically convert the PDE into a set of algebraic equation. Okay, I'll stop here for some time. If you have any questions, you can just ask me. Okay, so again, I would suggest that please have a look into this week's because these numerical methods. I understand if you are a BTech student, then these numerical methods are indeed something that is very new to you. And typically, most of the BTech colleges people even don't learn this numerical method. Typically, they start learning these things in their masters. But it's very good that if you are exposed to this numerical method at least in your pre-final year to final year of your BTech, then this becomes very much easy when you if you plan to at least if you so so people use these numerical methods everywhere. They use this in industry, they use this in academia a lot. Okay, in research, these are like the backbone of solving your PDs. Okay, because as you saw that this method of variable separation or this similarity solution, although these are approximate, it's very good that if you can frame your problem into this method of variable separation or your similarity approach, it's well and good. But if you can't, you have no other option but to use numerical methods. And in fact, all those softwares that, like, for instance, ANSYS or COMSOL, they uses these methods only. For instance, ANSYS uses finite volume method, COMSOL uses this finite element method, and and finite difference method is a little bit simplistic method, but you can anyway use it. You can just write your own, MATLAB code in finite difference method and solve a problem. For instance, you can just write this code in MATLAB. All these things we did, we can just write this code in MATLAB, and MATLAB will just give you the answer in seconds. Okay, so it's like initially learning it is little bit tedious. It's just that you need to learn the language of finite difference or finite volume methods. But once you know the language, once you know how to speak the language of this discretization, it will be just the bread and butter for you to just write this equation in MATLAB and just get the answers. Okay, so that's why these numerical methods are very powerful. And since this is an elementary course on heat transfer, we will not just go into the details of these numerical methods, typically because these are done in CFD courses. CFD meaning computational fluid dynamics courses, where where the sole objective of that course is basically to solve the governing equations using numerical methods. Okay, so that's the idea. So what I was saying is, I would suggest you to just have a look at the lecture series of this week, because it is very nicely explained how do you basically get this from this. Okay, so these things are very nicely explained, so you can just have a look at this, and then I think things will be much more clearer to you. Okay, so what we will do is, and similarly, just this is an example. So the problem, I think, that we just solved some few classes back using separation of variables. So this was our problem, where we had the temperature defined at these phases, and on these phases my temperature was just a function of x. Our objective was to evaluate the temperature on this on this whole phase. So we were just asked to evaluate p as a function of x and y. Okay, so the equation that we solved was basically the Laplace equation, that is del square t equal to 0, where it just boils down to the fact that del 2t by del x2 plus del 2t by del y2 equals to 0. Okay, now as we just saw, this equation can be written into an algebraic equation at any generic, let's say, I comma j node. Okay, so we saw that this can be written into this form as we just now saw. It can just be written into this form. Okay, so I'll just not write down the form here, but at least we saw that you can just discretize this equation into an algebraic equation. Okay, at the given I comma jth node. Okay, then what you do is, as I said, you need to write you just need to reciprocate this equation into all these nodes and basically solve for a temperature field at each and every grid points, that is at here, and at all these grid points. Now, as I said, okay, I would suggest that you solve this using two things at your home. So this is a homework for you. What you did is, we have already solved this Okay, we have already solved this using what is known as the method of, you know, so we have solved this using the method of separation of variable. What I would suggest now is try to kind of solve this, okay, using this numerical method. That use finite difference method to discretize this equation and try to solve the temperature field using this finite difference method. It may take some time for you, I understand, but at least when you will be, you will be used to like applying these finite difference methods and all, you will see the beauty of this of its application. You will see that like once you develop the code of using this finite difference method, your let's say you are solving it in Python or you are solving it in MATLAB, this will give you results in just some fraction of seconds. Okay, unless and until you take some, let's say 10 million to 10 million grids in the x and y direction, which you don't need. It's so since this is a 2D Cartesian problem, just by taking 1000 cross 1000 grids in the x and y direction will just suffice to getting a very accurate temperature profile in this discussion. Okay, so I will suggest you, so this is not, so of course it will take some time to learn this, basically how to solve this using finite difference method, but kind of like, just have a try on this and you will see the beauty of its application. Okay, so with this I will discuss one more thing and then I will call it a day. So we have seen now how to basically discretize how to discretize this spatial coordinate. That is, we know how to discretize del square t by del x2. We know how to discretize del square t by del y2. But what to do when we have time into our problem? Okay, this is something which is known as discretization of unsteady, equations, and we will see this into this in this discussion. Okay, so what we will do is we will learn how to solve the unsteady heat diffusion equation using finite difference method. Of course, we have already learned how to solve this using something which is known as the similarity solution that we just saw in the first half of this discussion. But now we will kind of do this using the numerical method using finite difference solution. Okay. But before that, if you have any doubts, you can just ask me. Okay. So basically, so I can frame this problem as, let's say you are having a rod, okay, and I expose, and I say to you that the initial temperature of this rod, okay, I'm assuming that the width of this rod is very, 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 very thin with respect to its length, just like the semi-infinite solution that we studied. So I'm assuming that the temperature of this rod for all x at time t equal to 0 is some Ti that we know. Let's say Ti is equal to 27 degrees Celsius or whatever. And of course, my this direction is my x direction, and I don't have any y because this is just a 1D problem. And what I say is that, so can you tell me how many boundary conditions? So this condition that I wrote here, this condition is known as an initial condition. Why it is known as initial condition? Because you are defining the temperature of this rod at time t equal to 0. And that's why this is known as an initial condition. But can you tell me how many boundary conditions do we require in order to close this problem? Yes? Yes, two boundary condition. Typically, because in space, your temperature derivative is second order in nature. So we need two boundary condition, and of course, we can define these two boundary condition at this face of this rod, and let's say at this face of this rod. Let's say I tell you that on this face, my temperature at x equal to 0, okay, for all time is some known temperature T1, and on this face, I tell you that at x equal to 0, sorry, this is not x equal to 0, let's say this is some x equal to L. For all time, this is some, let's say, T2. So once you know these things, okay, what you were asked is to basically evaluate what would be the temperature distribution in this rod as a function of x and t. So in other words, you need to find t as a function of x and t. Okay. Now, as we have seen, if you can somewhat establish the relationship between this x and t, you can use something which is known as the method, which is known as the method of this thing, what is called the similarity solution. Okay, but we will not do that in that fashion. What we will do is we will use these numerical methods to basically solve this unsteady problem. Okay, all right. So let's start off. So what should we do now? So the idea is very simple. We will divide this. This length, just like the 2D problem where we divide the entire 2D space into these grids. This is now a 1D problem, which is a relatively simpler problem. So what we will do is we will divide this problem into these grid points. Again, the idea is we will try to, find out the temperature at each and every grid points. And if my grid points are very close, this temperature will mimic the temperature field of an actual, of a continuous temperature field that we will get by solving it using a, let's say using a similarity variable approach. Okay, that's the idea behind this, behind the closeness of the grids used in finite difference method. The more close the grids are, okay, of course, the more close the solution will be to the actual solution. Okay, but then you can ask me that why are we not taking grids so close that the distance between them tends to 0? We cannot do that because this comes at an expense. Okay, the more the number of grids, the more the number of equations, algebraic equations you need to solve for, and that would require the more computational power at your end. So it's kind of a trade-off that we need to do, that yes, we need a more finer grid, but you know uh like, and also there is something which is known as grid independence, which means that after choosing the number of grids up to a certain level, or let's say up to a certain number, let's say I take 1000 grids here, and then if I increase the number of grids more, the solution would not vary much. And and the number of grids up to which the solution would not vary much is known as, so this is something known as grid independence. So people say grid independence is reached after, let's say, 1000 grids. Okay, which means that up to, let's say, n equal to 1000, which means if I take 1000 grids, then of course if I decrease the number of grids less than 1000, of course my solution will have error. But let's say I take now my number of grids to be 2000. This means that after n equal to 1000, even if I go for 2000 grids, my error in the temperature would not be that much, which now means that I have reached a stage which is known as the grid independence stage. Okay, so these are the things that you need to, also understand when you are using finite difference method, or, finite volume method, or any of the numerical methods that you use. But yeah, so the idea is we will just divide this, rod into this number of grids. And again, then what we will do is we'll pick any generic grid. Let's say this grid is I, and try to write down the equation on this grid I. Now this would be just I plus 1, and this would be just I minus 1, the other neighboring grids. Okay, so what I will do is I will just I will try to, write the equation on this ith grid, and the neighboring grids are I plus 1, and it is I minus 1. So if I now write del 2x by del x2, okay, on these grids, so this is just the zoomed in, this is just a zoomed in version of this. This is basically a zoomed in version of these points. Okay, I think you can appreciate that. All right. So if I now write this del 2t by del x2 in terms of these grid points, what it would be? So we just now saw it, right? It would be just t at I plus 1. We now don't have the y direction, so we don't need to bother about the y indices. Okay, it would be just temperature at I plus 1 grid minus 2 times of the temperature at I plus the temperature at I minus 1 grid divided by delta x squared. Okay, so this is something, no, this spatial discretization is something that we know. Okay, but the challenge is, what do we write for this? How do we write this term? Because we also have a one order derivative with time, right? So this is the challenge, because I cannot represent this in terms of these grids, right? Because all these grids are at a time step, let's say t. Okay, so any idea how do we do this, or any suggestions? So okay, spatial discretization is fine. I can write del 2t by, so remember I am writing this del 2t by del x2 at the ith grid. Okay, and if I write this del 2t by del x2 at the ith grid, the discretized equation basically looks something like this. That is fine. But how do I write this del T by del T at the ith grid? Any idea or any suggestions? Okay, so I'll tell you the answer. So the thing is, there are multiple ways through which we can write this del T by del T, that is a derivative of temperature with time at the ith grid. And these ways, so one way is known as the explicit solution. In fact, this is called the time explicit solution. There is also something which is known as the implicit solution. Okay. But for this discussion, we will be sticking to this explicit solution. And if I want to, write this explicit solution for del T by del T at the ith grid, I can simply write it as T at I when my time is T plus delta T, where this delta T is something that you need to define, minus T at I when my time is T divided by delta T. Okay. It is just a kind of first order marching in time. Okay. Where I say that my temperature at the ith grid point. So what I say is that the derivative of the temperature, okay, at the ith grid point is equal to the temperature at so it's equal to the temperature at the ith grid point when I march forward in time by a step delta t minus the temperature at the ith grid point when I have time t divided by the difference between the two time steps. Okay, so this way, of writing this del t by del t, this way of writing this del t by del t is known as, explicit. It's known as explicit differentiation, or writing the time derivative in explicit sense. Okay. Similarly, you can. We will not go into the implicit solution now, just for the sake of keeping the thing simple. But did you understand how basically this thing is written? Yes. Okay. Thank you very much. All right. So, explicit solutions. So, I would say explicit solutions are rather simple. Can you tell me why? Because I'll tell you, see, I have already defined, let's say at time t equal to 0, okay, I know that my temperature is Ti. So, this means that, let's say we are kind of evaluating this at time t equal to, let's say, some 1 second. And then what I can say is that I know my temperature at time t equal to 0. And if I know delta t, I kind of know my temperature at time t equal to delta t. So it's kind of like I know my temperature at time t plus delta t, which means that if I know my initial condition, then the derivative with time is just a marching problem in the forward direction if we use explicit scheme. And that's why these kind of problems are sometimes known as time marching problem. Okay. Again, I explain why this is known as time marching problem. For instance, let's say I want to know this del t by del t, okay, for the ith grid point. So what I will do is I will start off at time t equal to 0, which means that I know this value because at time t equal to 0, the entire rod is at some temperature t, let's say it's some t infinity, which means I know this, okay, and I know this, which means my my temperature at the next time step can be written as a culmination of these values. And if I know the initial value, the temperature at the next time step is just a marching forward of the of the previous temperature at the previous time step. So in this way, I can march forward in time to basically calculate the temperature at the subsequent time step. And that's why these kind of problems, so these unsteady problems, if you solve using numerical discretization methods, are known as time marching problems. Okay. Anyways, now if I just substitute this into my governing equation, I will basically get something like this. So del square t by del x2 is, so remember in del square t by del x2, I am evaluating all at time t. So now I will write this as t of I plus 1 evaluated at time t minus 2 times of ei evaluated at time t plus t of I minus 1 evaluated at time t, okay, divided by delta x squared, okay, and this is equal to what? This is equal to 1 by alpha, times del t by del t. So del t by del t becomes ti comma t plus delta t minus ti at t divided by delta t. Okay. Now, as I said, if you are evaluating, if you are evaluating all these terms, if you are evaluating all these terms at the previous time step, then this is known as an explicit, as I said, this is known as an explicit scheme. Okay. It's called explicit scheme because you already know the value of the temperature at the previous time step explicitly. And that's why by the name suggests, as the name suggests, this is known as explicit scheme. Okay. For instance, see, if I start from time t equal to 0 seconds, okay, and let's say I choose delta t to be some 0.01 second, then I can tell you what will be the temperature at t equal to 1 plus 0.01 seconds. How? Because this t now will be 0 seconds. I just need to calculate this temperature, and all these things are known. How? Because at t equal to 0 seconds, we know that the entire rod is at some t infinity. Now, similarly, in this way, you can determine what will be your temperature at t equal to, let's say, 1.01 seconds. Now, if you now want to determine it at, let's say, 1.02 seconds, you already know the temperature of all these things at 1.01 seconds. So in this way, you are just marching from one time step to the other time step. Is this clear or not? How this marching business is done in this explicit scheme? Or do I need to repeat it again? Because you already have an initial condition, you just need to march forward with time to basically, yeah, okay, I'll explain it again. Okay. So the thing is, when you are using an explicit scheme, let's say, so what you know, so you know that your temperature of the entire rod at time t equal to 0 for all x is some t infinity. Okay, which means, let's say I'm solving this, algebraic equation. Okay, forget about the spatial variables now, but let's say I'm solving this algebraic equation by marching forward with time. So what I will do is I will start my time loop, let's say t equal to 0. Okay, so at t equal to 0, and let's say I am considering my delta t, that is the time difference between the next time step, at, let's say, some 0.01 seconds. So at t equal to 0, so at t equal to 0, what happens is, if you have a look at this equation, this temperature will become what? So this temperature, I'll just name it like this. So this temperature will become Ti at t plus delta t, and I'm starting my time at t equal to 0, which means this would become at, let's say, 0.01 seconds. Okay, and this ti of t would be what? This would just be the ti at t equal to 0 seconds. Okay, and similarly, all these things would be the ti plus 1 at t equal to 0 seconds, and this would be ti at t equal to 0 seconds, and this would be ti minus 1 at t equal to 0 seconds. Okay, and what is the unknown? This is the unknown that we need to evaluate. What will be the time of the ith node at t equal to 0.01 seconds? Because we have chosen delta t to be equal to 0.01. Now, since we know all these things, so all these things are known, right? How do we know? Because we know the initial condition. The initial condition states that irrespective of any grid points that you choose, okay, your temperature is some Ti, which is, let's say this Ti is some 27 degrees Celsius, for simplicity, which means that all this information at time t equal to 0 seconds is known to you, and if you just substitute this value as 27 degrees Celsius, you will get your time at t equal to 0.01 seconds. So in the next time, so from t equal to 0 seconds, you have marched forward in time to get your temperature at t equal to 0.01 second. Okay, so now if you look at the next time step, let's say you look at t equal to 0.01 second, and you know the temperature from the previous time step, right? Which means next you can basically choose your delta t to be the forward. So your delta t will be what? 0.01 plus 0.01, which will be 0.02. So you will know your temperature field at t equal to 0.02 seconds. And similarly, you can do it for all the next subsequent time step. So the knowledge of the temperature field is achieved from the previous time step in order to calculate the temperature field at the current time step. Did you get what I was trying to say? Yes, okay. All right, thank you very much. So I understand this is the first time that you are learning such kind of techniques. So it will take some time, but you can do it at your end. Okay, and just Like do it at your end, and then things will be much more clearer. Okay. All right. So yeah. So I just messed it up, but just messed the things up. But so I hope this is clear. What basically is known as a time marching problem and all those things. But what I will now do is I'll just kind of simplify these equations to come out with something very interesting. Okay. So this would so what this would be is this can be written as t of I plus 1. I will write it again just for the sake of simplicity. And no, I will just write this t of I plus 1 at time t minus 2ti at time t plus t of I minus 1 at time t divided by delta x squared, and this is equal to 1 upon alpha, okay, times t of I at t plus delta t minus t of I at t by delta t. Okay, so what I will now do is I will take this delta x squared here, and then what I would get is t of I plus 1 at t minus 2 times of t of I at t plus t of I minus 1 at t. Okay, and this becomes equal to what? Alpha t delta x squared times ti of delta t minus 1 minus ti of t. Okay, something like this. Okay, now can you tell me what is this? I mean, does it sound some familiar with some non-dimensional number? We saw this in the last class. Alpha some time divided by the square of the length. Just think about it. What is this? So, can you tell me what was Fourier number? So, your Fourier number was alpha t by LC square, right? Yes. So, this number is kind of a Fourier number, and in fact, this is known as Fourier number in finite difference method. Okay. And in fact, this is 1 by this. So, you can write this. So, Fourier number is alpha t by LC square. So, this is 1 by Fourier number actually. What we can write is, you can write this delta x squared by alpha times delta t as 1 upon some Fourier number. This Fourier number is the Fourier number that is associated with, so the essence of this Fourier number is exactly same as the Fourier number we saw in lump capacity analysis. But this Fourier number is, you can see that this Fourier number, which is basically the ratio of alpha times the time step difference by the difference in the grid says, this is the Fourier number that is associated with the discrete, associated with the numerical, you can say it's a Fourier number associated with the numerical discretization. It is something like that. Okay, so if you write this in terms of the Fourier number, then this equation simplifies to t of I plus 1 at time t minus 2 times of t of I at time t plus t of I minus 1 at time t, and this would be equal to 1 upon Fourier number, okay, times ti at t plus delta t minus, this ti at t. Okay, now the idea is I will try to evaluate this time because this is the unknown. So when I start from t equal to 0 seconds, typically this is the unknown that I need to solve for. That is the time at the next time step. Okay, oh sorry, the temperature at the next time step. So what I will do is I can write ti at t plus delta t as how can I write? So this can be written as the Fourier number times ti plus 1 at time t minus t of ti at time t plus t of ti minus 1 at time t, okay, plus ti at t. And if I rearrange this, okay, if I just rearrange this, I can just write it at ti at t plus delta t. This is equal to the Fourier number times of ti plus 1 at t minus, sorry, I'll write this one here, ti minus 1 at time t, plus I will write this as 1 minus 2 times of Fourier number times ti at time t. Okay, and as I was saying, so this will be much more clearer to you how this time stepping is done. Okay, first let me just box this expression. So as I was saying, okay, just pay like a little attention here. So as I was saying that how do we get the temperature at the next time step? So what we do is we start off, one second, sorry. So this t is in the superscript, okay? All right. So we start off, by, so we start off from the t equal to 0 seconds. So can you tell me at t equal to 0 seconds, is the right hand side known or unknown? So at t equal to 0 second, is this right hand side a known quantity or an unknown quantity? Think about it and can you tell me? So at t equal to 0 seconds, this becomes t of I plus 1 at 0, this becomes t of I minus 1 at 0, and this becomes t of I at 0. So can you tell me, is it a known or an unknown quantity? Yes, it's a known quantity. From where do we know this known quantity? I mean, how is it known? So this is known from the initial condition, right? So we saw that repeatedly, that because I know my initial condition, because I know that at time t equal to 0, the entire rod is at 27 degrees Celsius, which means that at time t equal to 0, this quantity is known. And now, if I, let's say, choose delta t as some 0.01 seconds, which means just by using this expression, because Fourier number is just known, you know delta x and delta t. So delta x is basically a difference between two grids that you can decide on your own, and your delta t is also the difference between the two time step that also you need to decide. Okay, so once you fix your delta x and delta t, you fix your Fourier number, and you know these temperature values at time, t equal to 0, which means you now know your ti at time t equal to 0 plus 0.01, which means from this, you know, what do you know? You know your ti at 0.01 seconds. Now, when you move on to the next time step, your next time step would be what? Your next time step would be, let's say, at t equal to 0.01. Okay, you basically know all these things, right? Because from the previous time step, you know the temperature. So this means you know this. So at t equal to 0.01, you can now find out your ti at 0.02 seconds. Because you know, so so for the next time step, you know the values of the previous time step. And this is the same marching thing that I was trying to say. So this is basically the same marching problem as I was, trying to indicate it. Okay. All right. So now did you understand a little bit? Because so this method of expressing the unknown time as a function of the known time is known as an explicit scheme, because you know the temperature value at the next next time step explicitly in terms of the known values at the previous time step. Okay, and that's why this method is known as an explicit method. Okay. Uh, did you a little bit understood like how do we basically march forward with time? Yes. Okay. All right. So I'll discuss one more thing before closing this session. So that is, since this explicit method, as you can see, it's an easy method because you just need to march forward with time. So when things become easy, there are also certain certain what they say. So if things are easy, it doesn't always remain easy. That's what they say. Okay. So this explicit method has certain limitation. Since this is just a marching problem, okay, I will not go into the details of this limitation, but you need to understand that this explicit method works well when this 1 minus 2 times of Fourier number, okay, this, one second, I just, okay, so I'm just writing it correctly only. Okay, so what I was trying to say is this explicit method works well in the range. So there is a certain range of Fourier number where you can actually use this explicit method. And if your Fourier number exceeds this range, then you cannot use the explicit method and you have to go for other methods. Like, so there is a method which is, so there is this implicit method. Okay, there is also a very famous method which is known as Crank-Nicolson method. So it's in between the explicit and implicit method. This Crank-Nicolson method is known as CR method. Okay, using its short form. But we will not discuss all this method. But all I want to say is that if you are using explicit method, there is a certain range of Fourier number to which you can use the explicit method. And the range is that your 1 minus of 2 times of Fourier number should be greater than or equal to 0, which means your 2 times of Fourier number should be less than equal to 1, or your Fourier number is less than equal to half. Okay, so remember, this is true for a 1D scenario. Okay, so the idea is that if your Fourier number, so this is for an 1D problem, a 1D unsteady problem. So for an 1D problem, what you need to do is you need to first calculate your Fourier number. Your Fourier number is alpha delta t by delta x squared, and you choose your given delta t and delta x. And if your Fourier number is less than half, then you can be rest assured to use the explicit scheme. Or else, if your Fourier number is greater than half, your explicit scheme would give error in the result. Basically, your explicit scheme would basically blow up and it will not give your correct solution. Now, so Fourier number less than half is the criteria for a 1D problem. For a 2D problem, let's say you are solving this problem, del squared t by del x2 plus del squared t by del y2 equal to 1 by alpha del t. So you need to do the same discretization that we did now if we are using an explicit scheme, and then the criteria of Fourier number will come out to be your Fourier number should be less than 1 by 4 for a 2D problem. Okay, you can do it at your end. Just discretize these equations, okay, in the x and y, just how we did it in the previous example. Okay, use this explicit scheme that you know the temperature at the previous time step and you just march forward with time. Okay, then you will see that the criteria of Fourier number is basically equal to the fact that your Fourier number should be less than equal to 1 by 4 for a 2D problem. And I think this is one of the questions that the assignment has asked you this time, that you will find it in your assignment. So these things you need to remember. So finally, this criteria so when you are using an explicit scheme, okay, so if you are using an explicit scheme, the criteria on this Fourier number, that your Fourier number should be less than half if you are using a 1D problem, and your Fourier number is less than 1 by 4 if you are using a 2D problem. This criteria is known as CFL criteria. Okay, this criteria just says that if your Fourier number, if you are using explicit scheme, your Fourier number, which is the ratio of alpha delta t by delta x squared, okay, this should be less than a certain value for your scheme to to perform accurately. If not, you need to use other schemes like the implicit scheme or the Crank-Nicolson scheme and so on and so forth. Okay, so with this, I would end the discussion on today's numerical methods. I mean, solution to heat diffusion equation by using numerical methods. I understand this may be since I expect that the audience of this course is more or less the BTech students. So I understand that this might be the first time you are getting exposed to certain kinds of algebra or certain kinds of things. But trust me, like if you just do these things 2-3 times in your subject, or let's say if you are taking a more advanced course on computational fluid dynamics, these things will be just people say as like bread and butter for you. Okay, and once you make a habit of like solving this equation using writing codes in either MATLAB or Python, things will be much simpler to you, and you will see that your results are you will get tremendous results by using this. And the beauty of this numerical method is that it does not have any limitations on the boundary conditions that we have. It applies to all the boundary conditions. Only that there are certain criteria when you are solving an unsteady problem, for instance, the CFL criteria and so on and so forth. But remember, if you're solving a steady problem, then there is no such criteria. Just like how we saw in the previous example. Okay. All right. So any questions or any, like, I'll be happy to explain things once again, like if you ask me to explain it again. But at least now you should understand how do we march forward in time and how the knowledge from the previous time step is used to basically calculate the temperature of the ith node at the current time step. And then for the next time step, we use the temperature of this current time step to get the temperature at the next time step. So this marching that we are doing is known as time marching. Okay. And this is a like strength, you can say, of the explicit method, that you just need to know what is the initial time, and that is known from the initial condition. But it comes with a price. The price is that your Fourier number is, so it sets a limitation on the Fourier number, and this limitation is known as the CFL criteria in typically in in CFD language. Okay. All right. So any questions? So did you understand at least some bit of it, like on how these things goes on, when we try to solve it numerically? Yes, we have not done one thing. So far we have just learned to basically discretize the equation, but our job is not done there. Okay. After you discretize the equation, basically writing the algebraic equation, you need to form the set of algebraic equation into the matrix form of this sort, some A matrix times X equal to some B matrix. And basically you need to solve this X matrix. This X matrix will store the temperature values at each and every node points. And you just need to take the inverse of this matrix to get the temperature value at each and every grid points or node points. Okay. But we have not done this here, keeping in mind the fact that this is just a preliminary heat transfer course. But again, this idea will, so when you learn, further courses on numerical methods and CFD, these things would be helpful to you. And then you can see that, oh, okay, I at least learned some things of this in my heat transfer classes. Okay. All right. So any questions? Uh, Still, like when you are learning this at your end, and if you find any questions, always feel free to like post it in the discussion forum, and I'll be happy to answer these questions. But if you don't, it's like if there are no questions, like thank you very much for attending this class. I hope you have learned something on numerical methods, and from next week onwards, we'll move into what is known as radiation heat transfer. Okay, this ends conduction here. Still, if you have any doubts in conduction, okay, you can always ask. But from next week up to the next 4 classes at least, we will, learn, we will start off with radiation heat transfer. Okay, this ends conduction heat transfer, and we will start off with radiation in the next class. Thank you very much for attending. I hope you have learned something. We will meet it in the next week at the same timings from 3 to 5 p.m. on Saturdays. Thank you very much, and see you next time.